Okay, so welcome to the next talk, which is to introduce Revela, the game changer tool for decompiler of smart contract. So Revela allow you to decompile move-based bytecode, so it can recover like 100% of the smart contract deployed on Aptos blockchain right now. Okay, my name is Nguyen and Quynh, and I'm representing the team today. And sorry that my co-speaker Nguyen cannot make it today. Okay, so Revela was developed and maintained by VeriChain in partnership with Aptos Labs, with some grant from Aptos Foundation. So big thanks to Aptos for supporting the Revela project. Okay, so our tool Revela Decompiler have been already released with the full source code. You can access to the online compiler at the rest revela.verichains.io, or you can get the full source code from the GitHub at the rest github.com/verichains/revela. So here is the agenda of my talks. First, I will introduce a bit about some background on the Move smart contract, and then we look into details of how the Revela was built. And after that, we have some very quick demonstration, and we have some future plan. And after that, finally the conclusion. Okay, so Aptos is a blockchain built around language for smart contract named Move. And you can see here on the screen some very simple smart contract written in Move. And Move is a very advanced language designed from scratch for smart contract. And they have some features like statically typed data, which means that you need to declare on the data type at the when the program is built. And resource oriented, which means that they focus on ownership and access control of the resource object inside the smart contract. And finally, formal verification built-in, which means that you, as a developer, you can write your constraint to verify and really confirm that the code really does what it claims to do. So looking at the code on the left side, you can see that Move is very similar to Rust language. So here we have one module, which is okay, let's say one smart contract. This one will be deployed at the REST 12, and the name of this module is TC11. And this smart contract has only one function, which is public function, named foo. And foo is a function that returns some value of the type unsigned integer 64-bit. And foo doesn't take any input parameters. So inside the code, you can see that I suppose it's very friendly language. We like here we assign value 0 to variable I, and here we add 1 to variable I and assign that to the x variable. And then you have a while loop. This while loop runs until as long as x is under 5. And inside the while loop, we add 1 to x and assign that to y. And then you have another nested loop. So as long as y is still greater or equal to 0, we have the loop. And inside the loop, we have some other calculation, like assign some value to the z variable, add 1 to y, and there's another nested loop. So as long as z is not equal to 7, we do something inside. And finally, okay, outside this loop, and finally we do some calculation and return the value. And yeah, this is very simple function to show you how the Move language can be used to write a smart contract. Okay, so we, as a developer, you write smart contract in Move language, but we cannot put the source code of our smart contract up to the blockchain yet. We have to compile the source code So we use a compiler provided by Aptos to build the source code on the right side, and the compiler returns something like a binary file on the left side. And after that, we upload the binary file to the blockchain, and we call that binary file bytecode file. So on the left side, we see the bytecode format, bytecode form of the smart contract on the right side. So Move bytecode has some very interesting features. First one, Move bytecode is based on stack design. And second, it uses a 3 arrays code intermediate representation. So each, let's say each move instruction has 2 input, and we do some calculation and we write the result to the third output. And what makes Move bytecode very interesting is that the bytecode of Move retains many high-level information. So for example, inside the Move bytecode, in the binary file, you can still find the information like the module name, the structure definition, and all the dependencies. For the function inside the Move bytecode, you can see that function also retain many high-level information. Like you can find the name of the function, you can find all the arguments of the function, and all the data types of all the arguments. And the only exception here is that the bytecode do not keep the name of the arguments. That's the only thing that's missing. And inside function, we can have many local variables, and the bytecode also keep the data type on the local variables, except that it doesn't keep the name of the local variables. And finally, the branch target is no node compile time, so Move do not support dynamic dispatch design like in Solidity or EVM. Okay, so now we have the source code. We build the source code using the compiler. We get back the bytecode. And the question is how to understand the bytecode. So Aptos provides something like disassembler tool. So you can run the disassembler tool provided by the blockchain, and we feed in the bytecode binary file. And at the output, we can see all the disassembly of the Move. So you can see here that given the source code I showed before, in the disassembly, you can see that this code has 4 local variables, and all of them are unsigned into the 64-bit. And you can see that the code has many basic blocks, from B0 to B1 to B2 and until B12. And each basic block is organized so that the code enter the beginning of the block and only exit at the end of the block. And each block can branch to another block. So for example, here the B1, it does something like, it does some comparison. So based on the output result, if the result is false, it goes to array 54, which is block B12, block 12. Otherwise, it fall through to the next block, which is B2. Okay, so let's say we go to the Aptos blockchain, we get some smart contract. We try to analyze, we try to understand how the contract works, right? So before Revela, what we can do is that we feed the bytecode to the disassembler tool, and we get back the disassembly like I showed in the last slide. But we can see that the assembly code of Move bytecode is very unfriendly, very hard to understand, very hard to analyze. The other thing is that when many projects deploy a smart contract on the blockchain, they only upload the bytecode. They do not upload the source code. So without the source code, we have many issues. For example, you want to analyze some smart contract on chain, right? Without source code, we cannot see easily there is in the backdoor put inside the smart contract. And without the source code, it's very hard to perform the security audit. And finally, it's also hard to really verify that the code does what it claims to do. So that's why we build Revela. Revela can be used to decompile the smart contract bytecode, so we can recover the source code, which is very close to the original source code. And what makes the Revela special is that the output of Revela is a valid source code. And after that, we can take this source code to feed it directly into the Mu compiler. Okay, so looking at the high-level design of Revela, you can see that Revela is, as a decompiler, is quite similar to the compiler. So you can see that both compiler and decompiler, they take some input and they translate to something at the output. So the difference here is that for the compiler, the input is high-level source code. The output is something like low-level form, like maybe machine code or bytecode for some virtual machine. But the decompiler is different here. So the input for the decompiler is a bytecode, which is low-level form of the code. And at the output, we try to recover the high-level source code. For the design of the compiler and decompiler, they are quite similar. They both consist of front-end, middle-end, and back-end. So front-end try to analyze the input and leave it to some intermediate code. Intermediate representation code. And after that, the mid-end will perform some optimization. And the output of the back-end we will send to the back-end. And back-end will try to rebuild, try to restructure the high-level source code from the code sent to it by the middle end. Okay, so when we design Revela, we realize that the design of Mu really makes some impact to the design of our decompiler. So you can see here, for example, we compare the design of the traditional decompiler with the Revela. We can see that many problems that happen in the traditional compiler, we don't have that in Revela. For example, in the traditional compiler, they need to separate code and data, right? But in Revela, we don't have that issue. In the traditional decompiler, for example, you want to decompile the machine code, right? The level machine code. They have the concept like pointer or offset. Revela do not have that kind of concept. Declare data. So Revela do not need to declare data because we can recover all of those information from the Mu bytecode binaries. We do not need to recover the function parameters, function returns. We do not need to analyze the indirect sum or indirect cons because those concepts either do not exist in Mu language, or we can get all of those information directly from the Mu bytecode. We do not need to perform type analysis for the same reason because Mu bytecode retain all the type data. But there's still many things to do. You can see that the design Mu make it very easy, quite easy for Revela to implement because we can skip many traditional issues. But we still need to restructure the source code from the low-level bytecode. We still need to understand and perform medical optimization. And we need to recover the structures like loops or branch condition like if then else. So it's easier, but it's actually not easy. There's still many things to do. So here is the input and output of Revela. You can compare. So on the left side, we have the original source code, which I show you in the beginning of the presentation. And we view the code on the left side, and we feed the binary, the Mu bytecode to Revela. And at the right side, we get back the decompile source code. And you can compare the code on the left side written by Revela with the code on the left side, which is original source code. And we can see that many things similar. Like we keep all the information like function name, function data type, and all the code inside are very similar, except that because in the bytecode we do not have the original name of the variables, so we need to like propose something. So on the right side you see that on the left side, for example, here the variable name is I, but on the right side is the v0, for example. So Revela consists of 3 components: front end, middle end, and back end. And because we do not have much time, so in this talk I focus on the most interesting component of the Revela, which is the back end. So in the next slide, I try to explain how we build the control flow graph and how to build some code statement from the low-level bytecode, so you can recover the high-level source code. Okay, go back to our example. We have the move bytecode, and you can recover the assembly code, right? That's what you can see on the screen. So we have the many blocks from B0 to B12. And each block has many instructions, and one block can branch to another. So, okay, here on this slide, I break the blocks into multiple rectangles, and I put each block into one rectangle, and I connect them, so you can see better how you can build a graph. So here is what we call is a sequence connection of each block. So we connect block 0 to 1 and to 2 and so on in the physical order. But however, in the reality, one block might not really branch to the next physical block, right? So we need to perform some control flow analysis to really see how one block branch to another. So we can see here, for example, this block can jump to this block because we have the branch here, right? If the false, the result, the previous calculation is false, it goes here, right? And this one also B7 can branch to B10, and B10 can go back to B4, for example. So here is our blocks. We connect together using sequence S and jump S. Okay, look into one high-level source code example. So on the left side, we have some very simple code. We have the first block is to check some condition. If the condition is right, we go inside this block, which execute F1 function. If condition is wrong, we go to this block, which execute F2 function. And finally, get up of all of these checking condition blocks, we go to F3. So we have few blocks. Block 0, block 1, block 2, and block 3. And we try to connect them, B0 to B1, B2, and B3. So we have something like this. B0 can branch to B1, B1 can branch to B3, B0 can go to B2, B2 can go to B3. And there's no connection between B1 and B2 because two branches of the if checking condition cannot go to each other. Okay, here's another example so that we can have loop in the high-level source code. So here we have few blocks B0, B1, and B2, right? So we go into B0, and then B0 can go to B1 inside the loop. And after the loop, we go from B1 to B2. But you can see here that B1 can go back to the B0. So from the low-level basic block structure, you can see that we have a loop here. So that's why you can recover the high-level structure like loop from the low-level code like bytecode. Okay, so here go back to our example. Here's how our basic blocks are connected. So block 0 to 1 and 2 and go on. And 4 can go to 5 or 4 can go to 10, for example. So on. So you can recover all of those information. How basic block can connect to each other based from our analysis on the low level bytecode. Okay, so here our final graph that consists of many basic blocks and how they are connected together. Now we try to recover the high level structure of the code that can have like loop, that can have if condition, that can have branch of if then else, and it can have like break statements to get out of the loop, for example. So to do that, we perform some analysis for to understand how the code are linked together. So we try to build the topo short and strongly connected components because they are very helpful for us to generate the high-level code in the next step. So here, for example, in our graph, right, you can see that the code enters at block 0 and exit at block 12. So we have the first two components, A and C, and in the between, you can see that block 0, we go to block 1 and do something inside, and there are some path go back to block 1, which means that we have a loop from block 1 to block 11. So the code is structured like this. We have block A, which is block 0 here, and we have block C, which is block 12 here, and in the between you have a loop. Now we go on to continue to analyze block from 1 to 11, right? So you can see that we enter block 1, but block 1 can exit to block 12 immediately, which means that block 1 is something like break statement at the beginning of the loop. Right? So the structure of the SC is like this. We have block A, block B, block C, and block D. And we have the code like this. This one is block 0, and we enter the loop. And inside the loop, we have the first statement is a if condition, and it can break out immediately. And after that, we have another few other blocks, and we realize that, okay, this one is block 2. Block 3 is this one. And after that, we see that from block 4, 5, 6, 7, 8, 10 to 9, we have a loop here. Because there's a path to come back to block 4. So we have a loop here. Consists of block 4 to block 10, right? But you can see that block 4 can exit immediately. So which means that block 4, which is the first block of the loop, is a break statement. So we sum like if condition is break out the loop immediately. So now we look into the remaining block, which is from 5 to 10. So it's very similar. You have inside the loop, right, you have block 4, block 5, and block 6. And then we see that from block 7, 8 to 9, it loop back. So this one's another loop, nested inside the previous loop. And because block 7 can exit immediately, we can see that block 7 is actually another break statement with some if condition checking. So the remaining block is 8 and 9, right? And because we can see that 9 can break out the loop, so that means that at the block 9, you have another break statement. Yeah, so that is how Revela can rebuild the high-level structure of the code, which is a control flow. You can see, you can have the loop blocks, you can recover the break statement and so on. So the next thing is that how to recover the code statement. For example, in this code, right, we have the if condition. Check something, and based on the output, you can break out the loop. So how to recover the code statement inside the if condition statement here. Okay, so to do this, we use something very similar to Simulink execution. So for the example, we go back to our example, and here we look into the two blocks, very simple, block 0 and block 1. You can see here, block 0 has many instructions inside, and block 1 has only 4 instructions. And for these two blocks, 0 and 1, we look closely into every instruction inside each block. For example, this instruction, what it does is that it load value 0 to the bottom, to the top of the stack, right? And the next one, the instruction 2, it says the stack, the value of the top of the stack to the local variable named local 0. And the next one, it load the value from local 0 back to the top of the stack. And the instruction 3, it load the value 1, the constant number, to the top of the stack. And finally, the instruction 4, it the value of the true value inside the stack, which is the top of the stack. It pop out, actually it pop out true values of the stack here. And it add two numbers, and finally it say it back to the top of the stack. And for the instruction 5, it say the value from the 8th instruction back to the local variable 1, right? And we go on to the block 1. Firstly, it load the constant number 1. No, it load the local variable to local variable, and it loads the value of the stack, the top of the stack, to the local variable 1, and after that, it load constant number 5 to the top of the stack, and at the instruction 8, it pop out these two values in the stack and compare them, and based on the result, it can go to the arrest 54 if the result is false. So we understand every instruction in these two blocks and what they do. And the next step is that we build something like a symbolic value. Symbolic and value for each of those variables. So here, for example, when you load 0 to stack, right? We have one symbolic variable named CUCT40, and the value is 0, right? And for the next one, this one saves the top of the stack to the local variable 0, and actually here it pops the top of the stack out, so the stack become empty here. And for the next one, we load the top of the stack to the local variable 0. So we have another symbolic variable named T0 here in the symbolic stack, and so on. So like this one, we load constant 1 to the stack top. So in the symbolic stack, we have two variables T0 and CUCT41, right? And this one, we add these two numbers. We pop out these two symbolic variables from the stack and add them and put back to the stack. So after this, in the stack, we have only one variable, which has the value T0 plus CUCT41. Yeah, and so on. You can see is how we build the symbolic stack for every instruction. So the last step is that how we build the high-level code statement from the all of those analysis. So here's what we do. We only look into the instruction that say value to the output. So here, for example, this one say the value to the output, right? So we can recover the code statement, which is assign 0 to T0. And go on, this one say something to the output, right? So we can recover the high level source code here as T1 equal to T0 plus 1. And finally, this one does some comparison and branch. So we can recover the high level source code, which is to compare T1 to C use T4 true. And if it's true, it go if it's true, it go to the arrest 54. Okay, so go back to our example. We have two blocks, B0 and B1. And we try to recover the high-level source code from B0 and B1. Okay, so for B0, right, we recover two code statement, which is assign 0 to T0 and add 1 to T0 and assign to T1. And for this B1 block, we realize that this one is the first statement inside the loop, right? So we recover the information here, loop and the if condition and break. And we go one step further. You can see that the if statement break immediately as the first statement of the loop. So we convert loop and if break to the while loop, which is easier to understand, right? Okay, so that's how we Revela can build the control flow, how we can recover the code statement at the high level source code level. And here are some very interesting examples. So you can see how we compare the source code, the original source code, with the output of Revela. So here, for example, on the left side, at the top, we have this function, foo, right? Foo take one input parameter, which is x variable, and it return unsigned integer 64 bit, and it does some calculation inside. And you can see that on the left side, the code is actually very, it's not optimized. It does many things complicated, but it's not optimized. And the interesting thing is that if you compile the code on the left side using the Aptos compiler, you have the move bytecode, which is not very well optimized at all. So Revela actually tried to recover all the code, but after that it tried to optimize the code. So on the right side, you see that the code is much cleaner than the code on the left side. So see the example? At the bottom is very, very similar. We can recover the source code, and at the same time we can optimize the code, so the code is more cleaner. So here's another example, very similar. You can see that all the code on the left side, the right side are similar, but on the right side we do something to make the code more clean. For example, in this checking condition, right? It assign 1 to A and return A immediately. So in our decompiler, we just return 1 immediately. We don't need to have an extra variable for this case. Another case here is the abort instruction. We decompile and we rewrite it to assert, so the code is more clean and more easier to understand. Here's another example. You can see that the code is very similar, but I think it's easier to understand. For example, here we can return the value. Okay, let me see how this one does. Oh no, Okay, in this case, actually the code on the left side and right side are very similar. But the right side, because we do not have the original name of the variables, so we propose something like V0, V1, and V3, and so on. Okay, so we already tested Revela on all the high-level code of Aptos. We compile the standard lib contracts in Aptos to get the move bytecode, and we decompile back, and we can confirm that all of the code can be recovered successfully. Okay, so here's a very quick demonstration. Okay, so here we have the example. In the example, you have the contract name TC11, right? And I can run Revela Decompiler, and I point the decompiler to this bytecode. And at the output here is the recover source code by our decompiler. Thank you very much. And at the same time, we deployed Revela as an online tool. So here's a very quick demo. You can see how the online tool works. So here, right, you can see that we can look into many transactions from the Aptos blockchain. And we can see that many smart contracts do not have source code at all. So for this case, for example, here. So in this case, people deploy the contract to the Aptos blockchain, but without source code. And what we can do here is that we copy the account address of that contract, and then we go to the Revela online tool at the address revela.verychange.io, and we just paste we just copy the account address of that contract into this box and click sign to decompile. And after that, you can sign in with maybe Google account or GitHub account. And then inside Revela recover all the modules inside that account. And on the left side, we see all the module. And you just click into each module. And on the right side, Decompiler return the source code decompiled from the bytecode of that module on the left side. Yeah, so here we can confirm that we can recover all the source code of the module, and we find the function of that transaction in source code. Okay, so here's our future plan. We plan to continue to maintain and develop Revela, so it can be up to date. It can be updated to the new features of Mu language, and we plan to introduce more advanced features for the code analysis. And for now, Revela only support Aptos blockchain, but there are few other blockchains that also use Mu language for smart contract. So we plan to extend Revela to support other Move-based blockchains. Okay, so here come conclusion. Revela is the decompiler, so we can decompile Move bytecode, and we can recover the Move source code with the decompiler. And the return source code is the valid source code, which means you can actually fit immediately the source code to the Move compiler, and it can view again. And Revela bring transparency and trust to deploy smart contract. And because we can recover source code of every smart contract on Aptos blockchain, so Revela can be very helpful for the auditors to audit the security of the smart contract of all the already deployed smart contract on Aptos. Yeah, so that's my talk. I'm happy to take questions now.
So I have a question. Could
Yes.
particularly the optimization techniques be applied to other languages? Like, could you use it on things like Ghidra or other decompilers?
Actually, Revela just use some, well, let's say we use traditional techniques. It's not something special. And it won't come from textbook. But you can see that from the slide, you can see that because of the design, how the Mu language is designed, how the Mu bytecode is designed, it's easier for us to build Revela because there are many things we don't need to show, like compared to traditional machine code, for example. But otherwise, we use as well textbook technique for the compiler to build Revela.
I was just thinking mainly the optimization, because once you already have a decompiled, your optimized version was much nicer than the original.
Yeah.
Thanks. I have a question. So is within the scope of Revela to end up with a contract that could be recompiled?
Yeah. Right.
Have you done it?
Yes.
And the second question is, after you recompile it, have you compared the bytecode and does it save gas or is it expensive?
Okay, that's a good question. Okay, here go back to this slide, for example. Okay, compare the code on the left side and the right side, right? Left side is original code. Now we compile the code on the left side, we get the Mu bytecode, right? Now we feed the Mu bytecode to Revela, we get back the cleaner source code. Now if we compile the cleaner source code, we get back another bytecode, right? So we compare the first bytecode with the second bytecode, because the second bytecode comes from cleaner code. And the Mu compiler Aptos do not really do many optimization. So the bytecode true is more clean. It's shorter, it's smaller, it's better. Yeah, I suppose, yes. Less gas, for example.
I have one question for the decompiled code. So sometimes you use explicit and sometimes implicit returns. Is it by intention, or like when do you know if it's the actual value or the reference to the address of the value?
Yes. So what's the question? I don't know.
Yes. So sometimes it's explicit and implicit in the decompiled code. So when do you know which one is which?
Okay, we do some analysis inside the bytecode to see that. Yes, there are many information that you can see from the bytecode. And so for those you don't really need to do many analysis because the information is already there in the bytecode.
Okay, if there's no other questions, thank you.
Okay, thank you very much.